There's one other problem semi-related to sorting in the sense that we'll reuse the partition subroutine that we had used for quicksort. We can apply this in order to help us solve the selection problem. So the selection problem is that we're given an unsorted sequence of n elements and some integer k, and we want to find the kth smallest element in that set. So for example, we're given this unsorted sequence here, and we want to find, let's say, the third smallest element in the set. One way we could solve this just kind of straightforwardly is by sorting already. So if we were to sort this list, we would get the following sequence, and then from there we could count up, here's the first, second, and then third item. So 5 is the third smallest element in this sequence that we were given. Now we can sort in big O n log n time. Remember that we can only do faster than this if we can guarantee that our keys are integers and that they're within a particular range, which is a pretty specific restriction that in general, if we're talking about just an arbitrary sequence, we can't guarantee that we have that our integers are small enough. So we could sort in n log n time and then count up to find the kth smallest element. But we want to figure out if we can do any better than that without sorting, really. Just being able to figure out what the third smallest element is, or any number, the first, second, third, fourth, whatever number between 1 and n, find the smallest element in that set, the kth smallest element, without actually sorting that sequence. So this encompasses a variety of problems since k could be anything. So for example, if k is equal to 1, we're finding the smallest element in that sequence. This is the same as finding whatever the minimum element is. If k is equal to n, so we want to find the nth smallest, so this is the same as finding the maximum since we have n elements. Or if, let's say, we were to pick k is n over 2, taking the floor or ceiling appropriately, then this would give us whatever the median element is. So this encompasses a wide variety of problems. So we want to figure out if we can solve this selection problem faster than what we could do just by sorting all of the elements in the sequence and then counting up k spots, because if we have to sort, we know already this will require n log n time. And we can do this with the quick select algorithm. So this works very similarly to quick sort, but keep in mind we're not sorting our sequence. We just want to find the kth smallest element. So instead of sorting it, we're going to use a part of quicksort, not the full quicksort algorithm, just the partition method. This will give us, this is essentially a prune and search type of algorithm. We'll see, so you've seen one other prune and search kind of algorithm, which was binary search. Prune and search just means we have some sequence, we're looking for something. In this case, we're looking for the kth smallest item. And with the prune and search paradigm, this is we have some way of effectively saying, okay, for this entire sequence we're given, we don't have to look at the entire thing. We can kind of somehow reduce this so that we know the item we're looking for doesn't belong in a portion of this sequence, and we can reduce it to a different portion. And then, again, reduce this sequence into maybe somehow we determine the element we're looking for doesn't belong in this part, and we can just kind of prune the search space of where we should look for some item in our sequence. So quick select is a kind of prune and search algorithm. We're again looking for the kth smallest element, and how we're pruning our search space is we're going to pick a random element which belongs to our sequence, and this is our pivot element, and we're going to use this pivot in order to partition our sequence into, similarly to how we did with quicksort, we're going to partition all elements into everything which is less than our pivot, equal to our pivot, and greater than our pivot. So just one by one we can take this element x, our random pivot, pick a random index between the beginning and the end of our sequence, use that item as our pivot, and then just one by one compare every element of our sequence to this pivot. And if it's less than our pivot, we put it in L. If it's equal to our pivot, we put it in E. And if it's greater than our pivot, we put it in G. So that partition part is the same. But what's different is, unlike quicksort, we're not going to recur on both L and G. Instead, we're going to pick one of them and determine which one of them we should recur in based on where we know the kth smallest element will be. So we have, here's the original sequence we're given. We have X is our random pivot that we selected. We're going to use this to partition our sequence into, here are all of those items less than our pivot, equal to our pivot, and greater than our pivot. And then we're looking for the kth smallest element. So that means if K, what we're given, is less than or equal to however many items we have in L, we know that, let's say we have exactly this many items. This is the cardinality of this sequence, so the size of this sequence, these vertical lines here. So if we have, let's say here, we've got 3 items in L. If we're looking for the first, second, or third smallest element, we know that we have here the 3 smallest elements in our entire sequence. Then we know that either first, second, or third smallest element will be somewhere in L. So in that case, we can recur and look for that kth smallest item in L. We know it won't be in E or G. We can only focus on L. So if this number K, where we're looking for the kth smallest element, if this number is less than or equal to however many items we have in L, then we can recur directly on L. But if it's larger than however many items we have in L, let's say, for example, we're looking for the 5th smallest element, and we have only 3 items in L, then we know we have the 3 smallest items here, which means the 5th smallest item will be somewhere outside of L. So we have 2 options here. Either it belongs in E or it belongs in G. How do we know which situation we're in? If we were to add up together how many items are combined in both L and G, so this is the size of L plus the size of E. If K falls somewhere in between there, where we've got more, K is larger than however many items we have in L, so we know it's not in L, but it's no more than however many items we have combined between them. So let's say, for example, to fit that the number of elements that we have in this sequence, let's say we're looking for the 4th smallest item. And we've got 3 items in L, 1 item in G, and 1 item in E, and 3 items in G. So if K is equal to 4, we can exclude that the 4th smallest item isn't going to be in the first 3 smallest items, but we know we have 4 items total between L and E, so that means our 4th smallest item will be somewhere in here. So if we are in this case, then we're done. We can return our pivot element X. And even if we had more items in E, this doesn't matter. Because they're all in E, this means they're all the same. They're all equal to X, equal to our pivot. So we can return any one of them since they're all the same. So this is a kind of good instance in which we found exactly that item that we're looking for, and it's our pivot item. Okay, now in the last case, we find that for the kth smallest item we're searching for, we can exclude that we know it's not in L and it's not in E because K is strictly larger than however many items we have in L plus E. So this is this situation here. When K is too large, then we know that we're going to recur in G, that kth smallest element will be in here somewhere. But when we recur in G, we have to take into account that we have a smaller sequence now. And not only that, in this smaller size sequence, we've gotten rid of the first L plus E many of smaller elements. So in this case, when we recur in G, since we got rid of, here we have 4 smaller elements than in G. We've got 3 in L and 1 in E. Let's say we were looking for the 6th smallest element, and we had this partition. We know we're going to recur in G because 6 is larger than the number of items we have in L, which is 3, plus the number of items we have in E, which is 1. So we've got K is larger than 4. But when we recur in G, we're no longer looking for the 6th smallest element in G, because we just got rid of the first 4 smallest elements. So in G, instead of looking for the 6th smallest element, we're now looking for the 2nd smallest element. So how we come up with that new kind of K value when we recur is this is whatever we had our K value was before minus however many items we just got rid of that are smaller. So this is however many items we had in L and however many items we had in G. So algorithmically, this is, we take our sequence S, we want to find in that sequence the kth smallest element. So we pick a random pivot, maybe it's this one here. We use that pivot to partition our sequence, so you can refer back to the quicksort slides to see how this partition works. This is just, we scan one by one each item in our sequence, compare it to our pivot element. If it's less than our pivot element, it goes in L. If it's equal to our pivot element, it goes in E. If it's greater than our pivot element, it goes in G. And then we return those lists L, E, and G. So we just scan one by one each item in our sequence, comparing it to the pivot item. Once we have these lists now, we check to see, based on this value of K, how this compares to however many items we had in L and E. So if it's less than or equal to how many items we had in L, then we're going to recur in L, and we're still looking for the kth smallest item because we didn't get rid of any smaller items. They're all still there in L. If it's greater than the number of items we had in L, so we're not in this case, but it's still less than or equal to however many items we had in L and E combined, then we know that it will be our pivot item, that kth smallest item will be anything that we have in E, and since everything that we have in E has the same value, they're all equal to our pivot, then we can just return our pivot item. Or if we're not in any of these cases, meaning K is larger than however many items we had in L and E, then we're going to recur in G, which is everything which is greater than our pivot, but using a new K value, one which takes into account that we just got rid of the first so many smallest elements, which is the size of L and E combined. Okay, let's see an example of how this works first. Let's say we're given the following sequence S, and so this is our unsorted sequence, and we want to find in this unsorted sequence the 5th smallest element. And we want to do so without actually sorting our sequence, so we could sort everything and then count up 5 positions, but we want to do this in a more efficient way. And this is our quick select, using our quick select algorithm. So given this sequence, we're going to pick a random pivot, and let's just suppose this, what I have underlined, happens to be that random pivot that we chose. So we're going to break up our sequence now into L, E, and G. So L, we're just going to kind of one by one go through this. So 7 is larger than our pivot, 4 is larger than our pivot, 9 is larger, I'm going to run out of room here, 3 is equal, 2 is smaller, 6 and 5 are greater, 1 is smaller, and 8 is greater. So since we're looking for the since we're looking for the 5th smallest element, and we have here 2 items, and we have here 1 item, so we've got between L and E the 3 smallest items here, and we're looking for the 5th smallest item, then that means we know it's not going to be in L or E, so we're going to recur on G instead. We know we don't have to look in L and E. But when we recur in G, we're no longer looking for the 5th smallest item in G, because we got rid of the 3 smallest items. So now in here, we're looking for the 2nd smallest item. Why 2? We started off with, we're looking for the 5th smallest item, and then we just got rid of 1, 2, 3 items, how many items we had in L and E. So our new value, what we're recurring in G, what we're trying to find is the 2nd smallest item in G. So the 2nd smallest item in G is the 5th smallest item in this entire sequence S. So recurring in G, this is now how we get the sequence 7, 4, 9, 6, 5, 8 here. And we're looking for the 2nd smallest item in this smaller sequence S. Okay, so we pick a random pivot again. Let's just say we happen to pick 8 as our random pivot. So we're going to use that in order to break up our sequence again into the lists L, E, and G based on how they compare less than, equal to, or greater than our pivot, which is 8. So one by one, we're just going to go through that. We've got, starting with the beginning of our sequence, how it compares to 8. 7 is less than 8, so is 4. 9 is greater than 8. 6 is less than 8. 5 is less than 8, and 8 is equal to 8. We're looking for the second smallest element. And we've got now, here are the first 4 smallest elements, which means the second smallest element will be somewhere in there. So we're going to recur on this list. And we're still looking for the second smallest item in here because we didn't get rid of any smaller sized elements. So now we're recurring on the sequence 7, 4, 6, 5. This was the list L that we had from the previous step. And we're still looking for the second smallest item in this sequence. So we choose a random pivot. Let's just say we happen to choose 4. And we're going to partition our sequence again based on how each element compares with our pivot 4. So one by one, we've got 7 is greater than 4. 4 is equal to 4. 6 and 5 are greater than 4. Okay, so we're looking for the second smallest item, and between L and E, we have only the first smallest item, which means it's not going to be in L or E. We're going to recur in G. When we recur in G, we're no longer looking for the second smallest item. The second smallest item of this sequence corresponds to the first smallest item in G, because we got rid of one item which was smaller than it. So when we recur in G, we're now looking for the first smallest item. Again, how we got 1, how we moved from 2 to 1, we're recurring in G, so our new value of k when we recur will be whatever our old value of k was, which in this case is 2. We were looking for the second smallest item in this entire sequence, minus however many items we just got rid of that are smaller than the one we're looking for. We only got rid of, since we recurred on G, we got rid of however many items were in L and however many items were in E. And between the two of them, we have just one item. So we've got 2 minus 1, and this is how we get that new k value. Okay, so now that we're in the sequence S, we pick a random pivot. Let's say we just happen to choose randomly 5 as our pivot. So we break up our sequence now into everything less than, equal to, or greater than 5. One by one, we've got 7 and 6 are greater than 5. 5 is the only one equal to 5. We're looking for the first smallest item. We know that this is in E because we have here all items that are smaller than our pivot, and there isn't anything smaller than our pivot. And here's everything equal to our pivot. We could have multiple items here, but the only thing that's important is our k value, 1, is larger than the size of L, but it's less than or equal to however many items we had in L and E combined. So we've just finished. We found, okay, 5 is really that item that we're looking for. We can return that one. 5, the number 5, is in this sequence S, the first smallest item, the minimum, which corresponds to the second smallest item in this slightly larger sequence, which corresponds to the second smallest item in this sequence, which is the 5th smallest item in the original sequence that we were given. Okay, so that's one example of quick select. Now let's see, why is this actually more efficient than if we were to just sort items? Because notice, we're doing some things which are similar to quick sort in the sense that we're partitioning, but we're not recurring on the list L and G like quick sort would do. We're only recurring on one of them. So we'll look at the runtime analysis of this randomized quick select in the next video, and also see how we can make this efficient still without using any kind of randomization, using a deterministic algorithm instead. So if you have any questions, post on Piazza, reach out and let me know.